Our next speakers, I'd like to introduce our next speaker. It's Professor Michael Fisher. I think I heard a clap. No. So Michael is a professor of computer science and Royal Academy of Engineering. He's a chair of emerging technologies at the University of Manchester. Michael is an academic lead for CRADLE, the Center for Robotic Autonomy in Demanding and Long-Lasting Environments. He co-chairs the IEEE Technical Committee on Verification of Autonomous Systems, and his research concerns autonomous systems, particularly trustworthiness, and their application across robotics and autonomous vehicles. Michael.
Okay, thank you very much. Can you hear me? Does the microphone work? Excellent. Okay. Since I think I'm the first Manchester speaker here, welcome to Manchester, in case you haven't been before. Thank you. In case you haven't been before, the weather's always like this in Manchester. So come again. I've got a very brief presentation. It's only going to be 10 minutes. I'm going to pass on to Yann. I'm going to do a very general thing about robotics and AI that we have here, and in particular the CRADLE project, which you'll see a stand outside where we apply autonomous robotics in lots of different areas. Let me just mention two things about what I've heard already. So one is, I don't know anything about railways, but a lot of the problems to do with robotics and AI are similar in other sectors. It's not, some of the things you have are special, a lot of things are very general, and the same issues occur everywhere else. So if you're worried about using autonomous systems, AI, robotics, any of those things, you can always talk to other sectors that have used these things or are developing these things. The other aspect is this area, robotics and AI, the biggest growth industry is hyper misunderstanding of these things. And you've got to be careful in using this stuff that you understand exactly what it's going to do and exactly where to use it. Make sure it's used in the right areas. So that's just a general comment. Let me quickly go through presentation. So this university is quite big. There are a lot of people here working on robotics and AI. We have a very, very big center for robotics and AI. Over 100 academics across the university, not just engineers building robots, not just computer scientists like myself, but psychologists, philosophers, social scientists, how to live with robots, how to interact with them, how to make them do what you want. We have a very human-centered view of AI. So how can we make these robots and autonomous systems do what we want for the benefit of us, for the benefit of society in a safe and ethical and reliable way. So there's a lot of activities across the university. Since we're in an engineering building, I thought I'd do some videos, I'm not sure they'll play, but some videos of robots. So there's quite a lot of things like underwater robots. So for inspecting, no, they're not playing well. Imagine you could see some underwater robots there. Also ground robots for doing things like going into difficult to reach areas. So these are particularly robots using nuclear environments where you want to reach into areas where it's very hard to get a human in. Obviously it's dangerous, but very hard to get human in, but very hard to get traditional robots in. So you build robotic solutions for that. They're not going to move very well, these videos. Sorry about that. Okay, imagine they're moving. And obviously things like drones as well. So drone inspection, but also teams of robots. So this example here is where a drone carries another robot that goes down into a cave system or a tunnel system and inspects that. So a lot of these are sort of general purpose problems. So we have a lot of robotic systems being developed. We also, for those of you who are interested, we are the centre of the UK Robotics and Autonomous Systems Network. It's run from here, which is a collection of all the universities around the UK that are working on robotics and autonomous systems. So that's led from here as well. We have a lot of training schemes, and this is a new doctoral training scheme, which is a government-funded activity for the next generation of researchers looking into robotics and autonomous systems. So this Centre for Doctoral Training, I think, will fund 40 or 50 PhDs over the next 5 or 6 years, something like that. I wanted to mention that as well as building things, we want to make sure that these things will actually be used and applied. And so we work with regulators, standards bodies. We're involved in a lot of standards and policy activities to try and make sure that we're building the things that will actually get deployed and actually changing the standards and regulations to make sure we can get them updated for this new technologies. So the last thing I wanted to mention, I'm going to show a video in a minute, which is going to explain all these things much better than I can, is this CRADLE project. This is a large collaboration between the University of Manchester and Amentum. Amentum is, you probably know better as Jacobs, was before, now is Amentum, or bits of Amentum. A large engineering company looking at how we can take autonomous robotics, so robots that can be remote controlled, but can also go off on their own and do things, how we can use those in lots of difficult and unpleasant environments, or perhaps not so unpleasant, but places where people don't really want to be, or where it's very slow to use people. So obviously examples here like space, nuclear, underground, for example, a lot of infrastructure examples. So in this video, you'll see some examples of robots that are used for inspecting tunnels, for flying around to, again, inspecting various different areas, maybe even modifying things, maybe unscrewing bolts, different things like that, lots of different activities. It's up to you how you want to deploy these systems, but understanding how they work, how they should work, how they interact with people at some point, whether it's the people telling the robot what to do, or whether it's the robot reporting back what it's done after it's fixed it all, is very important. And how they might fail and how you might get them through regulators are all very important. So let's hope this video plays. If you want to hear more about Cradle, there's a stall exhibit downstairs where you can ask people questions, although some of them are in the room and should be downstairs manning the stands, but we'll get back there, yeah? Okay, let's see if this plays.
The world we live in is rapidly changing, and there is a need for us to adapt, using robotics and automation. The Centre for Robotic Autonomy in Demanding and Long-Lasting Environments is a prosperity partnership between the University of Manchester and Amentum, a global research centre led by the future needs of industry to help deliver economic, social and cultural prosperity through the use of robotics and AI. Through ambitious, creative and innovative research, we enable step changes in knowledge, understanding and technology, advancing the field from the fundamental to applications. With several programs for world-leading academics, scientists and engineers. Focusing on demanding, dirty and dangerous environments in sectors such as nuclear, space and infrastructure, we help to remove humans from harm. The Cradle Prosperity Partnership is supported by the Engineering and Physical Sciences Research Council and has 5 work packages. Components: improving the reliability of subsystems to ensure mission success. Architectures: designing verifiable software architectures for the reliable deployment of autonomous robots. Interactions: enhancing collaboration by addressing challenges in human and robot interactions for trustworthy and effective teamwork. Assurance: generating better evidence and arguments for ethical, safe and secure design and implementation. Demonstrators: showcasing next-generation solutions, leading to the deployment of robotics platforms in the real world. We make sure that the challenges we address combine fundamental research with industry needs through our unique Cradle Ideas methodology. By exploiting the joint capabilities of academia and industry, we can deliver immediate solutions, transferring state-of-the-art technology, whilst also identifying future research opportunities. Our vision is to create secure, reliable and resilient robots, deployed in demanding and long-lasting environments, assured by regulators and able to work seamlessly with humans and other robots. To make autonomous robotics the most advanced solution, addressing the challenges required to sustain and enhance our future world. Empowering UK and global industries with advanced robotics and autonomous systems. Cradle. Visit our website to learn more.
Or visit our stand downstairs to learn more as well. So that was the end of my brief presentation. I'm going to pass on to Yann now.
Thank you. I'll give a quick introduction. Great. Let me introduce Yann. Yann, after studying in France, Yann Bezin graduated with an honours degree in mechanical engineering from the Manchester Metropolitan University and joined the Rail Technology Unit at its inception in 1999 as a graduate engineer. He contributed to ongoing first international workshop on freight vehicle design in 2001. And then Yann joined the University of Huddersfield in July 2012 to set up the Institute of Railway Research together with former colleagues from the MMU. As part of the management team, Yann is the acting head of research at the IRR. Thank you, Yann.
Thank you very much, Mona. sorry, a bit lengthy introduction. So it's a pleasure to be here today and presenting to you. Normally I tend to talk about switching and crossing, but today I'll talk about robotics. As an assistant director of research of our groups, so the Institute of Railway Research. The work I'm presenting really is the work of my colleagues, Professor Gareth Tucker, and Hamid Reza Faham, who's here as well today. So we've got an exhibition stand downstairs, so please go and have a look. Well, briefly, the Institute, we've been in this field since 2012, and we do a broad range of research, applied R&D for industry, also direct consultancy. We're part of the UK Rail Research Innovation Network that was mentioned this morning by Dominic. Our areas of expertise are around vehicle and track dynamics, traction braking systems, pantograph and overhead system, all very mechanical, and within this we bring the data science, machine learning, smart maintenance and automation, and support development of technology through UCRI grant, for example. We have a number of facilities. Sorry, the text has gone wrong. Yeah, we've got full-scale buggy, roller, rig to do wheel rail contact studies, braking. We've got a motion simulator for train simulation. We've got a pantograph catenary interaction test bench, but also the smart maintenance facility. So it's the thing I want to talk about today. So that was a 1.8 million project co-funded by the Leeds region and the European Union Regional Development Fund. That was a 3-year project to set up a lab environment for robotics centered around rolling stock maintenance. So the aim was to improve the efficiency and effectiveness of rolling stock maintenance to meet future challenges. Yeah, that completed in 2023, but it's ongoing now. We've got build up links with industry, we've got applied projects, and we carry on with the facility. So this shows an example. We've got a clean lab with smaller robots that we use, and we start from there normally to demonstrate the feasibility of certain activities. Here's just a smaller scale printed version of a railway wheel with a brake disc that we want to try and remove. So we need to undo the bolts and then remove the brake discs and so on. So we tried this first on a small scale, and eventually we moved to the full-size lab that you see on the right-hand side. On the right-hand side at the bottom, you've got a pit, a small pit with a railway buggy, and the 2 industrial robots are moving up and down. Obviously, you would scale that back to a full depot along a train. But you can see the 2 robots can work in cooperation. There's one underneath in the pit that moves, so it just pops up in between the other 2. The robots can go and pick up the tools they need for inspection or for doing a certain action. You can see at the back the rack has moved towards the robot that's further back. Right, so the benefits of robotic, I guess we're all aware, but increased productivity, the accuracy and repeatability of the maintenance task, reduce the workforce exposure to dangerous and repetitive tasks, carry out the maintenance quicker eventually so we can release the train back and help with train availability. Also, we can eventually maybe connect this with maintenance management tools that we have and remote condition monitoring so that we can improve component life and resource usage. Briefly, some of the areas we contemplated and starting working on, maybe aspects of cleaning trains, doing inspection of the train, the components, the running gears, servicing the train, refueling and so on, doing the regular maintenance of checking torques on bolts and things like this, and potentially some of the train components overall. Now, if you go downstairs, you'll be able to have a look at this demo. Basically, the way we can interact with the robot. In this case, for example, we've got the VR headset, and the user can visualize the wheel that we are working on. You can select different menus of the actions you want to do, and then you pick the bolt that you want the robot to go and unscrew. So that's all, done. The interaction is done virtually through the headset. So you can be walking around in an environment with this type of headsets, like here, for example. Maybe you've got a headset and you can visualize the components. So here AI is being used to check the components are here in the right place. Dampers, axle box, the cap on of the wheel bearing, secondary suspension, the lifting hook. The number is the confidence of the AI in detecting a certain component, and that is there. So once this is all detected, then you can have a virtual asset with some menu of actions you can then perform and ask the robots to do. Okay, so I have 3 other examples I'd like to go through. So the first one is about pantograph testing. So normally a pantograph, so that sits on the top of the train, collects the electric power. Obviously they are mechanical systems, so they can fail. On the right-hand side, we've got a list of the things that you would want to find out and detect potential failures and how you would test them. So essentially, we've set up a test where we use the robots to do some of the typical push down. So normally that's done through a mechanical system or running the train through a lowering wire. Now you could do that through robotics and envisage that maybe you have a robot set up in your depot at the top of the train moves, and then you can check all the pantograph as you move along. So here the robot is pushing down. Essentially we're measuring the force reaction as a function of deflection. Now one of the advantage is that you can do that, but you can also use the robot to test the pantograph in different places or push it in slightly sideways to represent the different position of contact of the wire. So you can get actually more data than just a normal test. So you can start checking for the torque reaction in various locations. So you can then build the intelligence around this to detect certain specific faults. Another example is changing a brake disc. I showed a small video of a small mock-up model. So we had a student project last year coming from France, spending 3-4 months with us, and he developed that test here. So normally you work in cramped areas and it's quite difficult to do manually. So we had to change slightly the design to enable the robots to actually perform the actions. We first model this and we program the robot into Octopus, which is the software, the virtual software with the virtual environment. So we do that first, and then eventually we can realization. So we printed some of these parts rather than having real one because we had to make some changes. So the robot goes out and pick up the different pins in different locations. And eventually at the end it will completely free the disc brake and then remove it from here. So that's one small task. Obviously there's many more to go through the complete removal of the discs and so on. But essentially it proves that it can work. And then the final example is about refueling and servicing the train. So again, that's something we've been approached by an operator that they were interested in seeing how we can automate this process. So we talked about sanders, so we need sand, so we need to refill this every so often. The AdBlue as well for the diesel, add water to the train, so all these things require operation. So this shows you how you would maybe have a robot with a long linear guides running along the train in a depot, going to different position where it needs to perform the action. So again, we use the Octopus software to model all this. So you can see that's our lab. We made up some mock-up cabinets that would sit on the bottom of the train, and then the robots just perform the different actions. We had to make up some specific handles for the robot to pick up the different AdBlue nozzle, for example. And then eventually that's the real application with the industrial robots. So these tasks can be performed at quite fast speed as well. When it's going very full speed, it's quite impressive. It's quite a big robot, but when it moves fast, it's impressive. Okay, just the last slide for me in terms of the challenges regarding the implementation of robotics. Regarding rolling stock, obviously things are very much manual still. It's either technical or business challenges. On the technical side, just to point a few, we talked about brakes, for example, but every brake will come back with dirt, there'll be worn, damage. So the robots will need to adapt all of these challenges, conditions, and be able to adapt and try maybe slightly different things every time. So not just have a program which is very prescribed. Trains are not currently designed to accept robotics, so there'll need to be some changes around this. and so on. In terms of the business, well, yeah, there's clearly a lack of demonstrator to show the feasibility. So that's why this lab was set up, to really demonstrate the things that can be done. Yeah, there needs to be a clear leadership as well, and drive to involve, to invest in this area, to get a critical mass, to get it going. Okay, I'll just stop here. Thank you very much.